Hello everyone. In this video we are going to continue our discussion about Girdi algorithms, and we are going to learn about a very famous algorithm in computer science, and which is a Girdi algorithm called Huffman coding or Huffman encoding. Huffman coding is a data compression algorithm which is widely used in lossless compression. So what is the problem of compression? Assume that I have a text file that the possible symbols, characters that we have in this file is, for example, just restricted to 32 possible characters. Just assume all the alphabetic characters, some punctuation, a space, and white space. So the problem is, how can I encode this text file so that I used a smallest amount of space, yet I don't lose any information. The standard way for encoding is, so you might actually say that, okay, I'm going to have only 32 different characters, so I can compress it and represent it using bytes. I will define some binary representation, like the just only 5 bytes is going to be enough to represent 32 different characters. Right? So for example, A is going to be represented by 3 zeros, B 3 zeros and 1, all binary, different binary numbers between 0 and 31. Right? But how much space is going to take to represent, to compress this file? For example, if I have a 1 gigabyte of the file is actually 1 gigabyte of characters, I would need 5 bits for each character, so it's going to be 5 gigabits, for 5 bits for each character, and it's going to be 5 gigabits the whole space that it would take. But now the question is, can I do better than this or not? If the frequency of characters is almost uniquely actually distributed, so it means that for example, for all of different characters that I have, all of them are going to have the same frequency in that file. So I cannot do better than this. If I am looking for a lossless compression, I don't want to lose the data, this is the best probably thing that I can do. But what if I know that some information about the frequencies, that for example some characters like these characters are more common than the other characters, E, T, A, I, O, N. Usually when we are talking about English language, for example, these characters are going to be more frequent than some other characters, like X or Z are less frequent than the other characters, and these characters are more frequent, right? So can I use this fact that some characters are more frequent, some characters are less frequent, and use this fact to find some encoding, some way to encode all the characters so that in total at the end file is going to take less amount of space. The idea is that if I don't use fixed length encoding, then I can actually say that, okay, I would assign some codes which are shorter for the more frequent characters and longer representations for less frequent characters. So in this way, depending on the frequency of characters, I might get less space. I might use less space to compress the whole data. Let me show it to you using an example. Let's consider a smaller, a simpler problem. Just assume that all the characters that I can have in my file is restricted to these 6 characters, A to F, and I know the frequency of these characters. That A is the most frequent one, and these are the rest of the frequency for the rest of the characters. Okay, so if I use the fixed length representation, you see that I have only 6 characters, so 3 bits is going to be enough. So 1 gigabyte of characters, each one is going to take a code with length 3, so 3 bits multiplied by 1 gig, it's going to be 3 gigabits for the space. But what if I suggest to use a variable length coding like this one, that I only use 10 to represent A, and then the codes like with 3 bits to represent B, C, and D. These are 3 different encoding, and use 4 bits to represent E and F. So let's just calculate that how much space I would use using this variable length encoding. So you can use that I have assigned a code with the shortest length for A, which is more frequent, and longer codes for E and F, which are the less frequent characters in my file. So how can I calculate the space? The thing is, I can just multiply these frequencies that I know, this distribution that I know about the frequency, multiply by the total number of characters. So I know that 1 gigabyte multiplied by 0.45 is going to be the number of A characters that I have in the file. So what can I do is that, and then multiply it by this length, which is 1. So this is going to be this many bits for A, this many bits for B, and so on. So I can do the calculation, and this is the result that I factored out that 1 gigabyte, and the rest of it is just multiplying the length of the code to the frequency and get the summation over all of them. So the final result, as you can see, is 2.24 gigabits, which is considerably smaller than 3 gigabits using the fixed length encoding. So the whole idea is that we are looking for variable encoding instead of using the fixed length encoding. One issue with variable length encoding is that if I am using fixed length encoding, decoding is going to be pretty easy. So assume that I have this fixed length encoding, and I have assigned these different codes for these different these 5 different characters that I have. If I wanted to decode any string, I know that I should start it and getting every 3 bits, and just look at the table, find the corresponding letter. So this 3 bits is going to be B, then the next 3 bits is going to be C, the next 3 bits is going to be A. The algorithm is very easy for decoding, and you are not losing any information. The result is unique, pretty easy, pretty straightforward. But if I use variable length encoding, you might actually get some issue. For example, assume I have assigned this variable length encoding to these 5 characters, and I'm going to decode this string. How can I decode it? So let's look at this one. The 001 is going to be B, right? And then I would say that, okay, 0, 1 is going to be A, and then 1, 1, 0 is going to be D, right? But I can also actually look at this string and decode it in this way, that the first 3 bits is going to be B, the next 3 bits is going to be C, and the next 2 bits is going to be E. So now you can see that there is an issue with this variable length encoding. I can decode the result and get 2 different string. And this is an issue. This is called ambiguity. Not only the algorithm is very complicated, but also at the end you don't know what was the original file, and definitely this is not acceptable, right? So to fix this issue, one thing that we can do is that we should make sure that our variable length encoding is actually decoded uniquely. One way to fix it is to put some separator between the characters. So, for example, in this previous example that we had, if I put some separator, for example, I don't know, some different character, if I know that after each of these I put some separator, something like the encoding using Morse, I can actually get, the decoding is going to be very easy, very straightforward, and there is no ambiguity. But the issue with this solution is that it's going to take more space, right? Because for each character that you have in your file that you are going to encode, you need to have one separate, this separation symbol. So this is not really good idea to do the compression. It's going to waste some space. A different and a better solution is that if I make sure that in my variable encoding there is no prefix coding, I can assure that there is no ambiguity during the decoding. And what does this mean? If I look at the previous example that I showed you, the issue with the ambiguity was that if you look at the code for A and C, you can see that A is in fact a prefix of C. So that's why in some cases you can actually get a part of the string and decode it as A, or actually just get more bits and decode it as C. If I avoid prefix coding, so in that case I would make sure that my variable length coding is going to be decoded uniquely and there won't be any ambiguity. So if I fix this example and I assigned a different code for A and C using something like this, you can see that none of these codes are the prefix of the other one. So for example, E, you don't have any other code that starts with 1, 0, or you don't have any other code that starts with 0, 1, right? It doesn't have prefix coding. So now let's actually decode this string that I have. I know that 001 is going to be B. It can't be decoded in any other way. 01 is going to be decoded as D, and then 110 is going to be decoded as A. And there's no other way to read this string. Let's do it over another example. Again, you can see that in this coding that I have, I don't have prefix coding issues, so none of these codes are the prefix of the other one. If I'm going to decode this, so 10 is going to be decoded as L, 0, 1 is going to be decoded as E, then 0, 0, 0 is going to be decoded as U, and then 0, 0, 1 is going to be decoded as K. Okay? So far you have seen that we have solved that issue of ambiguity, but the algorithm for decoding might be not really easy to implement in this way, because you should actually keep reading. You saw that how actually I solved this problem. I started reading the characters one by one, and after reading each one, try to actually find something among the list of codes that I have. And if it is long, you can see that the time complexity is going to be really high, because after reading each byte, I need to again look back at all of these codes and find which one is going to be assigned. I mean, if any of them is correct. Otherwise, I should actually just go forward and get another character. So what can I do in this case? I mean, more efficient algorithm for decoding here is that I can represent the code using a tree, which is going to be a binary tree. You can see that these codes that I have has been represented using this binary tree. And all of the edges are marked using 0, 1, and something that I put as a rule is that always the left children, this is a binary tree, so each node is going to have at most two children, two edges going down, and always consider the left edge to be marked using as 0 and the right edge to be marked as 1. Now you can see that after I have represented the code, all of the leaf nodes are going to be all the characters for me, and started from the root, the path that you follow from the root to each leaf node is going to be the code for that character. For example, the code for A is 1, 1, right? The path from starting from the root is going to be this path. And what is the labels of the edges? It is going to be 1, 1, right? There is something nice about this representation. All of the leaf nodes are going to be all of the characters. There is a unique path starting from the root to each leaf node, and you are representing all of the characters. You are not actually missing anything. What else? The other thing is that the algorithm is going to be very simple to apply. When you are reading your string, you actually just started from the root node, and for each one bit that you read, you just follow the corresponding edge. That I started from here, the first character that I'm reading is going to be 1. The first bit that I'm reading is going to be 1, right? So this is going to go, let me actually use a different color. From the root, you start from the root, you read 1, and then you read 0. So that's it. You reach to a leaf node, and this is going to be your character. So L has been found. Then you you read the next character. This is going to be 0, and then the next character 1. So that's it. The next bit is 1. So the corresponding symbol that you found is E. Then you start reading again. So this is 0, then 0, then 0 again. You found U. So this time 0, 0, 1, you found K. The algorithm is much easier. Instead of looking at all of the codes each time. I am just traversing in the tree. This representation makes the decoding algorithm much easier. So it wrote actually the decoding algorithms in, verbally. It started from the root. You just read each bit from the file and you follow the tree and until you reach to a leaf node. And so that's going to be the character that you have. Another nice thing about this representation is that every prefix code, we call it prefix code, that none of the code that you have found for all of the symbols are going to be the prefix of the other one. Every prefix code will be represented using a unique binary tree. And every binary tree is going to represent exactly one prefix code. So far, we have solved the issue of decoding using a variable length encoding. We know what is the algorithm for decoding, and we know how to make sure there is no ambiguity in decoding. Now we have to actually get back to our main problem. How can we find the best variable length prefix code to make sure that we are using the smallest amount of space. Before I actually go back to the algorithm to find the optimal prefix code, I have to define some notation, which is we will call it average bit per letter. Using this example, just assume that I have an example that I have 5 characters, A, E, K, L, and U, in this example that I showed you here. And I know the frequency of them for example, in a specific file that I'm going to compress. A is the most frequent one, and the rest of the characters, all of them are going to have the frequency of 0.05. So for any set of characters that we know the frequency for them, we can define average byte per letter over any prefix code that we define for them. What is going to be this average byte per letter? It's just simply the multiplication between the length of the length of the code that we have assigned to each character multiplied by the frequency. So for this example, the average byte per letter is just multiplying, for example, the 2 letters for A, 2 letters for E, multiply all of them by the frequency, and this is going to be this summation. So on average, the number of bytes that I need per each letter is going to be 2.1 if I use a set of code like a prefix code like this. And in general, I'm going to represent average byte per letter using this notation, B of T, that T is going to be that binary tree that represents the prefix code for me. So instead of actually writing it in this way, I can say that I can represent it using a binary tree, right? So it's going to be corresponding to some binary tree, let's call it T, and I am representing the average byte per letter using B of T, which is going to be the summation of multiplying the frequency of each character multiplied by the number of bits that I'm using to represent it, or the depth of that specific, you can actually say that the depth of that specific leaf node or character in the tree. You remember that in the binary tree we represent the depth of each node to be the distance from the root. So for each of these, for example, the depth of A is going to be 2, exactly the distance from the root to this leaf node, the number of edges that you pass to reach from the root to this node. So now using this notation, I can define my problem very clean and neat. That we are looking for optimal prefix code that minimize average byte per letter, right? We are looking for a prefix code represented using this binary tree T with n leaf nodes, and we are such that it minimizes the average byte per letter. So this problem might actually look very complicated because the search space is very big, and the problem that you are solving is that you have a search space of exponentially different binary trees, and you are going to look for the optimal one. This might actually be very scary, and it's going to be even worse when you are thinking about it as this is going to be a greedy algorithm. How can I find the optimal choice in this greedy algorithm? So the search space is already very complicated. How can we approach to a problem like this? So I'm going to actually give you a couple of facts about the problem that makes it much easier to approach. The first thing is that in our optimal solution, if I'm looking for an optimal solution, I would know that we are representing it using, we are looking for a binary tree, okay? The optimal binary tree that we are going to find is going to be a full binary tree. Remember what was the full binary tree? In a full binary tree, all the nodes are either leaf node or a full node, which means that all the internal nodes are going to have exactly 2 children. Something like this one. So you can see that in this binary tree, all the internal nodes are marked in black, all the leaf nodes are marked in green. So except the leaf node that doesn't have any children, all other nodes are going to be full, or all other nodes are going to have exactly 2 children. And this this observation is easy to prove. The thing is, if there is any node in your binary tree, in your optimal binary tree, that only has 1 child, some pattern like this one, that for example, we only have 1 child, right? Instead of using, you can see that to reach from U to W, you need to actually pass V, and you need to pass 2 edges, right? I can basically just remove V and use exactly 1 edge instead of using 2 edges. Because V is not going to have another child, right? So I can simply just ignore V and use just 1 edge instead of 2. I'm not losing any information about the letters. Not only that, I am making sure that the length of the coding, the length of some of the codes are going to be shorter, because here instead of using 2 edges, I'm using 1 edge. Definitely this is going to be shorter, right? So this makes sure that in the optimal binary tree representation for your prefix code, there is no node with just 1 child. So this is going to be definitely a full binary tree. And if to make it actually more clear, look at this example. This example has that pattern that one of the nodes only have 1 child, right? If you are going to decode this string, you can see that using this binary code, you reach something, some solution like this. But if I remove this node and I replace these two edges with just one edge, the resulting tree is going to actually look like this, right? Now I can encode the same string here using a shorter code. Both of these S and P are going to have a shorter code, and the whole string became actually shorter. So this is the whole idea. Definitely in the optimal binary tree that we are looking for, the optimal binary tree is going to be a full binary tree. Another thing that we can conclude from this observation, another fact that we can conclude from this observation is that in the optimal solution, there are at least two leaf nodes which are at the maximum depth, and they are sibling. This is easy actually to prove again, because if you look at, anyway, some of the leaf nodes are going to have to be at the maximum depth, right? If you look at those leaf nodes as the maximum depth, we know that, okay, so there is going to be a tree, okay, and at some point you have a leaf node that has the highest depth. This is going to be the highest, the maximum depth. Maximum depth. Okay, so it is going to have a parent, right? And that parent is going to be a node which is an internal node. So it cannot be, this node cannot have only one child. It definitely is going to have another child. So now you can see that if for that node that you have at the maximum depth, definitely there is going to be another one sibling for that, and that node is going to have exactly the same depth. And the thing is, these two nodes are going to have the minimum frequency because they are going to have the longest code, right? If you are assigning some other characters that has higher frequency to these two nodes, if you are, for example, E, or probably E is not a good option, for example, something like Z and X. If you are assigning some other characters that has higher frequency to these two nodes here, you can change them and replace them with the two characters that has the minimum frequency and get a better average byte per letter for your tree, right? So this is easy to prove that you are going to have two leaf nodes with the maximum, at least two leaf nodes with the maximum depth, and they are going to have the minimum frequency among all of the characters that you have. So this simple fact is going to be enough for me to find the algorithm to solve the problem and find the optimal binary tree. The question that I have here for you is that we know in general that when we are assigning the characters for the leaf node in our tree, some of the leaf nodes are going to be at the lower depth, higher in the levels, and some of them are going to be at the lower levels or more depth. You are going to assign the more frequent characters to those letters at the higher levels, those leaf nodes at the higher level. And so, for example, if I have a tree like this, so those letters that are assigned to the leaf nodes at the higher level or less depth are going to be more frequent, right? More frequency, and these letters are going to be less frequent words. So that's it. I'm going to use all these facts to give you the algorithm. This is something that we already discussed about, that those two leaf nodes at the maximum depth are going to have the lowest frequency among all of the characters that we are going to assign to the leaf nodes. So this simple fact was enough for David Huffman to find the algorithm to create the optimal binary tree for the prefix coding. It's actually nice to know that he has done it as a course project when he was doing his PhD at MIT. This is a very famous algorithm. Actually, you should know that this is a very famous algorithm that used in many compressing compressing applications, softwares which are used right now. So let's jump to the algorithm. The template of this algorithm is very simple. The whole idea is that we should always look for the two less frequent characters, get them and create a tree using them, and replace them in the set of characters with a dummy node that has the frequency is going to be defined as the summation of these two. So let's explain the algorithm over this example. This is the original example that I showed you. Assume I have 6 characters A to F and I know the frequency for them. The idea is that I would create, for example, you can create a node for each of these letters, a leaf node corresponding to each one. I'm going to create the tree at the end, right? So let's create a node for each one. Then take the two nodes corresponding to the letters with the less frequent, the minimum frequencies. So I would take E and F and I create a tree like this. This is a small tree. Then I would add a dummy, so instead of E and F, I'm replacing the set of nodes that I have with, adding this tree. So basically, I don't have E and F anymore. I have this new node, which is the parent of E and F. And the frequency of this one is going to be, I'm going to write the frequency, close to that. So the frequency of this one is going to be the summation of frequency of these two. It is going to be 0.14. Now you should actually think about the fact that, okay, I have all these small binary trees. I know the frequency for each one. Take the two that has the smallest frequencies. So if you think about it, it's going to be this one and this one. I would take them, create a larger binary tree using them. B, C, create a larger binary tree, and the frequency of this new letter that I have is going to be the summation of the frequency of these two. This is going to be 0.25. So I can remove these two from the set. Now it's just like I have 3 characters. A, this dummy character here, and which has the frequency of 0.25, D, and this dummy character here. Now look at all of them and find the 2 that has the minimum frequency. So this is going to be D and this one. sorry, D and this character, right? I will get these two and I will create a binary tree using these two. So that binary tree is going to look like this. I would add a parent and I just added this. What is going to be the frequency for the parent? It's going to be the summation of 0.14 and 0.16. This is going to be 0.3. Okay, now I remained with only three nodes, right? One of them is A, the other one is here with frequency 0.2, and the other one is here. They find two with the minimum frequency. So these are going to be this one and this one. I can take these two and create another binary tree, put these two as the children of that. So this is going to be, I'm going to draw it here. B, C, here is going to be D, and here is E, here is F. Okay, so I can remove this, and before actually removing that, let's calculate the frequency for this one. This is going to be the summation of frequency of the other two. And that's it. We remained with two a smaller node. You can actually think about it as only A and this one. So whenever you have only two, you should take both of them, right? They're going to have the smallest one. So I'm going to take these two and create a new binary tree. A and this, and that's it. We are done with the creating our binary tree for our prefix coding. Now the remaining is just assigning the edges. Always give 0 to the left edges and 1 to the right edges. So now the code that I found for A is going to be 0. For B, it is going to be 1, 0, 0. For C, it is going to be 1, 0, 1. For D, it is going to be 1, 1, 0. For E, it is going to be 1, 1, 1, 0. And for F, it is going to be 1, 1, 1, 1. And if you calculated the average byte per letter, bit per letter, it is going to be 1 multiplied by 0.45 plus 3 multiplied by 0.13 3 multiplied by 0.12, 3 multiplied by 0.16, 4 multiplied by, just get the summation of this, so 0.5 and 0.09, right? You can calculate the average byte. I don't actually have the answer for this one, but anyway. If I'm going to write down the algorithm, I can write it in a recursive way, something like this, that just assume that S is going to be the set of n different letters. We know the frequency for each one. Just assume we have them as a f of 1 to n. This is a recursive algorithm, so I need a base case for that. If the number of letters in S is going to be 2. So this is the base case, right? You just have 2 characters, you create a binary tree. This is going to be simple. You create a binary tree, assign each of them as a label of a leaf node, and this is going to, you just return that, assign the edges to 0 and 1 in this binary tree, and you are done. If the length of S is greater than 2, then you find the 2 characters in S with the minimum frequency. You remove these 2 characters from S, let's just call it S prime, and then add a new character, which was in fact representing as the parent of that Y and Z. And the frequency of this new character W is going to be the summation of the frequency of Z and Y added to S prime, and basically just recursively call this Huffman coding algorithm again over S prime. So you are passing a shorter set. S prime is going to have, if you have n letters in S prime is going to have n minus 1 letters, right? You remove the Y and Z and you replaced it with this dummy character W, which basically represent the parent of the Y and Z. And let's just assume that you are done with that, calling that Huffman of S prime. It is going to return a tree for you, right? In this new tree, wherever is the W is going to be a leaf node, right? Get W and replace it, add 2 children for W as with the labels Y and Z, and just assign the label for the edges as well. And then it is going to be the result of the final tree, and you return the tree. And the algorithm is very nice, and you can, I would recommend you that exactly apply this recursive algorithm over the example. You will see that it is just this example that I showed you. I mean, the process is exactly the same, but the process of creating the tree is reverse. You are, in fact, you are reducing the number of nodes and then expanding the tree from the higher level. Instead of actually creating it from the bottom to top, you are creating it from top to bottom using this recursive algorithm. It's just nice if you try to apply it over an example and trace this recursive algorithm. What is the time complexity of this algorithm? So if I look at all the cases here, the time complexity is constant. The time complexity of creating this tree using 2 nodes is constant for the base case, right? Finding the minimum frequency letters here is going to take some time. So that is going to be O of n or theta of n to find the minimum frequency, right? And then you remove it from S, create a new set, then you call the Huffman encoding again. So in total, the time relation that I can find for this recursive algorithm is T of n is equal to, what is the size of S? Size of S is n, right? The number of letters. The size of S prime is going to be n minus 1, right? N minus 1 letter in S prime. So this is going to be, the size of the problem is going to be 1 smaller plus this cost, which is going to be theta of n, right? If I solve this recursive relation, I will get T of n will be equal to theta of n power 2. You can actually do it using the substitution. So this is a simple recursive relation to solve. But what can I do to make it better? Instead of this cost that I have for finding the minimum frequency, that looking over all of the characters to find the minimum frequency, instead of keeping it as a list, I can use a priority queue. I can use a heap, binary heap. So finding the minimum frequency nodes is going to take, instead of O(n), I can replace it to log of n if I use a priority queue, if I use a binary heap, right? Finding the minimum in a binary heap is going to take log of n. So if I solve this recursive relation, I will get to theta or O of n log n. I think this one is also easy to solve, but you just need to do it, just do the substitution approach. T of n equal to T of n minus 1 plus log n. You can keep actually replacing T of n minus plus log n minus 1 plus log n. If you actually continue this, you will see that at the end, T of n is going to be equal to log 1, log 2, this summation until log n. So this is the summation of all these logs. I can write it as log of the multiplication of all these numbers, right? The multiplication of I from 1 to n. So this is going to be log of n factorial, right? And we know that log of n factorial is in theta or O of n log n. So we get an algorithm with time complexity O of n log n to find the optimal binary tree for the prefix coding. Okay, now let's actually solve this example. This example asking that if I use 3 bits per character, a fixed length, how much space I would take, and can I find a better answer? We found an optimal binary tree here, right? I'm going to actually just calculate, using this one, find that how many, how much space, how many bits I need to compress if I use this tree. If I do the calculation here, average bit per letter is going to be 2.24, and multiply by 1 gigabyte of characters. In total, I'm going to use 1 gigabit using the Huffman encoding versus 3 gigabits if I use the fixed length coding, which is definitely better than the fixed length encoding. The last topic that I'm going to discuss here is the proof of correctness for this algorithm. In fact, we have seen those facts that end up to the algorithm for Huffman, but we need to prove that this is going to be the optimal, the tree that will be created using this algorithm, using the Huffman algorithm, will give us the minimum byte per letter, average byte per letter. So I can do it using induction. So the base case is I can do it using induction. The algorithm is recursive, so proof it using induction is the easiest way. The base case in the recursive algorithm was that if the number of letters you are going to create the binary tree for, that is 2, it is simple that the algorithm is going to give you the optimal answer because basically if you have two nodes, the optimal answer is just a binary tree like this, that each of the leaf nodes is going to be one of the characters, and the algorithm gave you exactly the same. The inductive step in the proof is that we would assume the Huffman algorithm give us the optimal binary tree using all values less than n. So if you have n minus 1 number of characters, n minus 2, whatever is smaller than n, the Huffman encoding definitely give you an optimal binary tree. Now we are going to prove that Huffman encoding is going to give you an optimal solution if you pass it n number of characters. So this tree T prime, which has n minus 1 letter, this is going to be the tree that the Huffman encoding gave me as a sub-solution here, right? The thing is, we are going to assume that T prime is optimal for n minus 1 letter. Now, if we replace it with one of the characters and created the T with, which is going to be a tree with n letters, n leaf nodes, this is going to be optimal, assuming T prime is optimal. So what is the relationship between the average byte per letter for B and the average byte per letter for, B of T and B of T prime? So in fact, in T prime, we found that node W and replaced it, which was, the frequency for W was the summation of frequency of two other letters Y and Z, right? If you look at the algorithm, basically the algorithm tells you to find W, which is a leaf node in T prime, replace it, add two leaf nodes to W as a Y and Z, right? So I'm going to exactly just expand this here. That the average byte per letter for whatever is the tree, so the tree looks like something like this is going to be the T prime. So whatever is the tree, somewhere at some point you are going to have that leaf node W. This is T prime. I am going to create T, which everything looks the same. The only difference here is that W became an internal node, and I'm going to add Y and Z to that. Okay, this is going to be T. So the average byte per letter for T is going to be whatever is the average byte per letter for T prime, plus I'm going to, W is not a leaf node anymore, right? So I'm going to subtract the average byte, the average byte per letter for W. I'm subtracting that. And instead of that, I am adding two more leaf nodes, Y and Z, right? That what is going to be the frequency for, I know the frequency for Y, I know the frequency for Z, and what is going to be the depth of Y and Z, whatever is the depth of W plus 1, this is going to be the depth or the length of the code for Y and Z. Okay, so I am just subtracting W. W is not a leaf node anymore. That's why I'm subtracting this part. And instead of that, adding the length of the code for Y multiplied by the frequency of that, and the length of the code for Z multiplied by the frequency of that. So I need to actually just expand this, and you will see that if I expand this, I know that this part and this part are going to be removed by this part. And the only part that remains is the frequency of y will be multiplied by 1, frequency of z multiplied by z. And so the result, the relation between the byte per encode, average byte per letter for t and t prime is that average byte per letter for t is the summation of average byte per letter for t prime plus the frequency of y and z. This is going to be the frequency of w. I can write it in this way, right? So now I am going to prove that if t prime is optimal, t is also optimal. To prove that, assume there is an optimal solution that we call it t star for n number of letters. And let's just assume that this answer has a better average byte per letter than the tree t that has been created using t prime in the Huffman algorithm. So it means that the frequency, the average byte per letter in t star is smaller than this. I'm going to prove that this is not possible. This is a contradiction. So if it is the case, let's actually find the two characters y and z in this optimal binary tree that we found t star. Okay, these are the lowest frequency characters for us, right? Let's just remove them from t star and create a new tree that we are going to call it t star prime. It will be something corresponding to what we have as a t prime, right? If I remove y and z, the parent of y and z, so let's just assume that this is a tree which is going to be t star. Wherever y and z appear, I'm going to remove them, and the result is going to be, they are going to be some leaf node, right? And we already actually showed that in the optimal, the first fact that we discussed, in the optimal answer, y and z should be, the two nodes with the lowest frequency should be sibling of each other. If I remove this one, if I remove y and z, I will end up to a tree that will look like this, right? This is going to be called t star prime. Okay, and this is going to be a leaf node in this new tree. So we know that it is, okay. So we know that t star prime is going to be a tree with n-1 leaf node. So if you have n-1 leaf node, you know that t prime is the optimal answer. This is the assumption, right, in our induction part. T prime is optimal. So for t star prime cannot be better than t prime, right? I know this relation is going to help. Because t prime is already optimal, whatever is the byte per average byte per letter for t star prime is going to be definitely greater than or equal to this. I'm going to add the frequency of fy and fz to both sides of this inequation that I found, this relation that I found. What I get is something like this, right? If I add f by 2 and fz, whatever I get for from this side is going to be this summation. I already know that this is going to be equal to average byte per letter for the tree t created from t prime by replacing that node with y and adding the y and z as a leaf node. And the other side here is going to give me the average byte per letter for t star prime. We already actually proved this relation. I'm exactly using this relation here. So the final relation that I got is that the b of t star is going to be greater than or equal to b of t. It actually tells me that t star is that optimal answer that we assumed, right? If the average byte per letter for the optimal tree is greater than or equal to the average byte per letter for the tree T that we created using Huffman encoding, it means that the tree created by the Huffman encoding algorithm is optimal. So Huffman encoding is in your textbook. In all of the textbooks, actually, it has been discussed. In the CLRS, this is chapter 16, section 3. In KT, it is chapter 4, section 8. And in DPV, it is chapter 5, section 2. Please read the slides after listening to this lecture. If you had any question, we can discuss it during the office hour.